Hello student, to the course of physics of linear and nonlinear optical waveguides. Today we have lecture number 30 and today we will going to study a very important topic which is modes in an optical fiber. So today we are going to learn modes for a step index fiber. So far we are dealing with the modes for planar waveguides. So today we will going to study the modes for step index fiber. So let me first draw the structure of the optical fiber. We had a core part, surrounded by a cladding. This is the structure, geometrical structure of a fiber. Where the refractive index profile is this for step index. So this is N1, N2 and the refractive index is N1, this is N2. So we have a cylindrical symmetry of this geometry and we are going to use this cylindrical symmetry in the Maxwell's equation to find out the modes, that is all. So for this kind of system, if I write the field, it should be psi r phi z t. It should be a function of r phi z because I am dealing with now a cylindrical symmetry. It should be divided into two parts. One is psi a, which is dealing with the r phi part, and a propagation part as usual with beta z minus omega t. So I have r phi dependency here and z and t dependency in the exponential term. So this is a definition, or this is a form of a optical field that is going to propagate inside the fiber, which has a cylindrical symmetry. Now we have the wave equation, which is of the form this. Now here this operator, the Laplacian operator, I should write in cylindrical coordinate. That is something we need to take care. So if I write this operator, it should be r phi plus this. This is a shorthand notation. So if I write this, that means I am eventually doing the partial derivative with respect to z like this, second order partial derivative. Now if I am going to operate these things over here, so I will have this quantity del square del t square psi, because I know what is my psi, I can write it as minus of n square omega square divided by c square and then psi. Because when I make a double derivative of this given field, the term here sitting should come out, the omega should come out as minus I omega twice. I should have a negative sign, and it is simply n square omega square divided by c square and then psi. And the first two part is simply this portion. I have a second order derivative with respect to z, and I know this is my field. So, if I do, it should be minus of beta square psi is equal to minus of n square k 0 square psi, where my k 0 is omega divided by c, free space propagation constant or wave vector. So, eventually I have this this is the equation I am right now having. Now, I can write this part in a expanded form. So, in expanded form, it should be del 2 psi del r square plus 1 by r del psi del r plus this is only this portion is this one plus the rest of the term that we already derived. Okay. Now, psi is something like psi a e to the power of I beta z minus omega t. Already we defined that. So, if I put this value here, then you can see e to the power I beta z omega t does not have any dependency of r and phi, and here it is only psi. So, I can write this equation in terms of psi a. So, it should be simply e to the power of I beta z minus omega t, and then it should be this plus whatever I have So, simply this term and this term will cancel up, and eventually we have this. Okay. This is the expression I have right now. Well, I can now make a standard procedure which is called the separation of variable, that it is a function of r and phi. So, I can make it as a function of r and big phi phi, which is called the separation of variables. I am making a separation of variables of that. If I now have the separation of variable by making a function of r and phi like this, and put this equation, put this solution in the equation whatever we have, then it is easy to show that I will have an equation like this. This is equation with respect to r, and on the right hand side I can have an equation with respect to phi only. Now, the left hand side of the equation is now as a function of r, and the right hand side is a function of phi only. Now, these two are equal, that means obviously they should be equal to some constant, and I write this constant at L square. I write this as a L square because just after a few minutes you are going to find that it will form a very well known differential equation if I write this constant at L square, only for that, because it can in principle it can be any constant. So, I write this constant in special form to have a special differential equation in our hand. So, now I have the radial equation, that means the equation related to r, as r square d2r dr square. So, only the left hand side I am writing, plus r dr plus r square k0 square n square minus beta square, then minus L square multiplied by r is equal to 0. Okay, this is my left hand side. I multiply this r here, so then put it back, and then I am having this equation. So, this is the equation, radial equation I am having. On the other hand, the azimuthal equation or phi equation, this is r equation. So, the phi equation should be something like this: d2 phi d phi square plus L square big phi is equal to 0. So, now I have two equations in my hand. This is the radial equation and this is the phi equation or azimuthal equation. and if I solve these two equation, then I can have the value of r and phi, and if I have the value of r and phi, then I can eventually have the value of psi a, which is the field distribution. Well, now I need to put some condition, because in our case we have the step index fiber. So, so let me write it. For step index fiber, what is the geometry of the step index fiber? So, if I now, okay, let me draw in a more correct manner, because now I am dealing with r. So, better to remove this portion, and so this is the refractive index as a function of r. This is my r, and this is a. This distance is a, which is the core part, and the refractive index is n1 here and n2 here. So, for step index fiber, this is the refractive index profile. So, once we know this is the refractive index profile, I am going to put this information here in this equation. So, when r is say less than a, function of in r is simply n1, a constant. So, that means this is inside the core. So, inside the core region I have this, and I will put this into equation, and if I put this into the radial equation, it should be simply this. Now, I write here this term in this way. Note it, I put the n1 here, because I know in this equation this n is now replaced by n1, and I write this r square multiplied by k0 square n square minus beta square as r square divided by a square, and then I multiplied another a square here. There is a specific reason for that, it will make my calculation a little bit simpler. Now, we introduce a variable, a parameter a u, which is a into k0 square n1 square minus beta square. Note it, u is a constant and a dimensionless quantity. So, better to write it to the power half. So, this is something which is dimensionless, and if I now write this equation in terms of u, then I should have this. So, r square d2 r dr square plus r square dr plus this portion, you can see this is my u square. So, I can write it as r square u square divided by a square, and then minus L square r equal to 0. This quantity R u divided by A, we write it as x, I rescale it as x. Then my R becomes simply x multiplied by A u. So, my dr dx should be equal to A by u. So, dr, so this is a variable of r. Now, I change this variable to x. So, this quantity I can now write as, using the chain rule, as this. Which is u by A. Okay, here it should be a smaller. So, it should be u by A d bigger dx. In a similar way, if I write the second derivative with respect to r, then it should be simply u square divided by A square d2 r dx square. So, this transformation I have, this is one transformation, this is another, which I am going to put in this main equation. If I put everything into the main equation, instead of r I put x A divided by u, this double derivative with respect to smaller I put this value and so on. If I do, then I am going to have something like x square A square divided by u square, then u square by A square d2 r dx square plus x A by u, then u by A dr dx. I am writing all the term explicitly so that you can understand what is going on here, and x square divided by . So, this is the equation I am having after transferring everything in terms of x. So, you can see this u square A square, u square A square, A by u, u by A, this term will going to cancel out, and I will have a very well known equation in my hand. This is a very well known differential equation. And I believe by that time most of you have already recognized this differential equation. This is the Bessel's equation. After putting all this effort, I find the radial equation can be represented in terms of Bessel's equation. So, the solution, once we have this Bessel's differential equations, Bessel's differential equation, once we have the Bessel's differential equation, after putting all these variable and all these terms, then the next thing is will be simpler because we know what is the solution. So, we are going to use this solution directly because now the solution of the differential equation of the radial part is known, that is. So, let me write this equation, equation 1. Another part is still there, which is the azimuthal equation. So, let me go back to my azimuthal equation. Or my phi equation. This equation is little bit simpler and easy to solve, because I know the structure of this differential equation, and this is this. Readily I have the solution, and if I write the solution, it should be a sinusoidal solution. So, it is a function of small phi, and I can write it as a constant a, then sin phi l plus another constant b cos of phi l. You can note that this equation has a phi symmetry. So, when now phi has a azimuthal symmetry, what is the meaning of azimuthal symmetry? So, if I look carefully to the fiber structure, so the core part, if I draw the core part, so this is the fiber core x and y, and whatever the solution I have here, if I go to 2 pi, if I make a round of 2 pi, then the solution will remain unchanged. So, that means phi of phi should be equal to phi of phi plus 2 pi. So, that means a of sin L phi plus b of cos L phi should be equal to a of sin L phi plus 2 pi plus b of cos and it should be the same thing once we have L is equal to say integer 0, 1, 2, 3 and so on. If the L's are integer, then this phi symmetry will follow. So, I have a very important information from this set, that L has to be the integer value having 1, 2, 3, 4. It is restricted to some integer value, discrete integer value. It is not a continuous, if this is not a constant with continuous values, it is a discrete values, and these discrete values are 0, 1, 2. So, eventually L is a integer. Now, I do not have much time to solve this radial equation. The next part is I am going to solve this radial equation. So, in the next class we will start from this Bessel's differential equation and try to solve the equation, try to put the solution of the equation, which are the Bessel solutions, and put certain boundary condition to find out that what should be the form of exact solutions. So, with this note I would like to conclude here. So, thank you for your attention and see you in the next class for the solutions.